This is Dr. Aravind, Professor, Department of EEE, Case Rangasan College of Technology. Today's class we are going to discuss about the induction type wattmeter, which is very important for measuring of AC power. Induction type wattmeter, it operates on the same working principles on which the induction type ammeter and voltmeter operates. Induction phenomenon, it can only happen in the alternating current systems. These instruments only measure the AC power. So, the induction type wattmeters are useful only when the supply and the frequency remains constant. Construction of induction type wattmeter, one electromagnet connected in a series with the circuit. So, the flux produced by this electromagnet is directly proportional to the current in the circuit. The second electromagnet in parallel with the circuit. Thus, the current proportional to the voltage of the circuit produces another flux in the second electromagnet. So, the place is a lightweight circular aluminum disc in between these two electromagnets. Fluxes of the electromagnet produces two eddy current in the disc. The interaction between eddy currents which the flux produces deflecting torque in the instrument. There are 2 or 3 copper rings fitted in the central limb of the shunt magnet. Due to this arrangement, the flux created by the shunt magnet lags 90 degree behind the circuit voltage. So, on the basis of constructions, there are 2 variations of the induction type wattmeter available. In one variation, the shunt electromagnet has a 3 limb. There are two limb hold the voltage coil and the central limb holds the copper rings. On the other hand, the series electromagnet has a 2 limb. Both of the 2 limb hold the current coil. So, in the second variations of the induction wattmeter series, a series electromagnet has a 3 limb. The central limb holds the current coil, whereas the shunt electromagnet has only 2 limb. There are yoke of the electromagnet holds the voltage coil. The pole faces have come closer. These 2 pole faces together are surrounded by the single copper ring. Let us consider the supply voltage is a reference, V as a reference voltages, I is the load current, in the circuit it is a lag reference voltages by theta, and it is have in the same directions the flux tangents created by this current load current is pi AC, and the angle between V and I, the reference voltage V and the load current I is theta. The pi AC is the flux created by the series magnet. Thus, the flux will be in phase with the current. The flux will be in phase with the current I. Shunt fluxes is is called as the pi SH. Is the flux created by the shunt electromagnet. Ideally, the shunt flux lag behind the circuit voltage V by 90 degree. The series flux pi SC of series magnet induces the EMF EAC, that is called eddy voltages in the disc. This EMF causes the eddy current IAC in the disc. Working principles, we can ensure that the disc is fully resistive. The eddy current IAC caused by the induced EMF EAC, series eddy voltages, it will be in phase with the supply voltage EM. So, we see that the eddy current IAC also lags the current I by 90 degree. The angle between series flux and the eddy current IAC is 90 degree. The shunt flux increases the EMF ESH in the disc. The induced EMF ESH lags the shunt flux by 90 degree. As we have already assumed that the disc is fully resistive, the eddy current ISH caused by the induced EMF ESH, it will be in phase with the EMF induced supply voltage or induced EMF. Hence, the eddy current ISH also lags the flux by 90 degree. So the two fluxes interacts with the aluminum disc. So the torque produced by the induction of the interaction of the current ISC and shunt flux is first torque 1, that is equal to K into ISC, ISH into cos theta. So ISC is the series current and ISH will be the flux caused by the series current on the disk, and cos theta will be the cosine angle between your ISA and pi AC. The torque produced by the induction of the interaction of the current ISH and flux pi AC is T2 second torque on the same disk, and there is constant K and shunt current and series flux lines, and the angle between your current and voltages is 180 minus theta. Cosine angle between voltage and the current is the cos 180 minus theta. So it will be going to produce the second torque is ISH, pi AC and cos theta, cos 180 minus theta. The expression of the resultant deflection torque is deflecting torque TD, that is equal to difference of the torque 1 and the torque 2 on the aluminum disc. So torque T, as we already stated, the T1 is K into ISC pi S into cos theta, that is constant into series current and some flux lines is created by the shunt current and cos theta, that minus K into ISH and pi SC and cos 180 minus theta, that is torque developed by produced by the interaction of the current ISH and flux pi SC on the disk, that is going to call as the T2. So now we can take the constant K outside, and the remaining equations inside inside the bracket, that is ISC pi SH cos theta plus ISH pi SC and cos theta. So K into K1 VA cos theta plus K2 into VA cos theta. So at the end, the cumulative flux linces of T1 and T2 will cause the deflecting torque, that is equal the final deflecting torque after interaction between T1 and T2 is K into supply voltage V and the load current I, and the angle between this voltage and the current is cos theta. So the remaining the constant K1 and K2 will be added together. So the final equations of the torque is TD is directly proportional to supply voltage V and load current I, and the cosine angle between V and I, that is equal to cos theta. It will be going to count the power factor of the meter, power factor of the load. This is nothing but the expression of the AC power. So that the deflecting torque is in induction wattmeter proportional to the power to be measured. So advantages and disadvantages of the wattmeter. Advantages: the scale is very long scale, and the freedom from the effect of the stray field. Effective damping torque, it will be going to the damping. This effective damping torque will going to hold the disc from grip. Disadvantages: changes in the temperatures cause the variation in the resistance of the moving element, affect the eddy current therein, and so the operating torque. The error due to this is in part of offset by a balancing effect due to the change in the temperature of the winding. So the causes of the temperatures causes the variation of the resistances, and it will going to affect the measurement. And the changes in the frequency from that of the calibration value causes variation in both the resistance and the voltage coil circuit, which is highly inductive, and also in the amount of compensation from the phase compensation circuit within the limit of the frequency variations met with practice on the mains. This last the error is not important. So that induction type wattmeter will going to will measure the AC power with accurately. Thank you.